In this video, we're going to look at the problem of finding the points on the conic section defined by the intersection of these two curves or two surfaces, and find the points on that conic section that are closest to the origin. Now, ideally, you might have seen this problem in class, or maybe we haven't got to it, or maybe we just didn't have time to get to it. We will talk about at least setting the problem up. And then we're going to kind of just jump to where we actually have the solutions because I don't want to do all that work right now. So notice that we have f. F isn't vector valued. We're going to write g in a way that's vector valued, but we're not there yet. F is going to equal, we'll say x squared plus y squared plus z squared. df equals 2x, 2y, 2z. And here's how we will write it. We'll write g as a vector valued function. We don't always do this, but it's going to be useful coming up soon. G will equal our first constraint function, and then our second one. So we're treating this as a vector valued function, and this will make, the reason we're doing this will be apparent soon. And then the matrix of partial derivatives for g, basically the stack of gradients, is going to be 2x, 2y, negative 2z, and then we'll have 1, 1, negative 1. So we have that. Now we can go ahead and do some stuff. So we would set up our system of equations. Since we have two constraints, we're going to have two lambdas. So we'll have 2x equals 2x lambda 1 plus lambda 2. So remember, it's first one times lambda 1 plus second one times lambda 2. Then we'll have 2y equals, so this 2y equals 2y times lambda 1 plus lambda 2. And we'll have 2z equals negative 2z times lambda 1 minus lambda 2. And then we'll have our two constraint equations. We'll have x squared plus y squared minus z squared equals 0. Then we'll have x plus y minus 2, or minus z equals negative 2. And that is certainly a lot of fun to solve. We are going to jump ahead to the solution. The solution of that is we're going to have the points. It looks like, I'm reading this from the book, negative 2 plus square root of 2, negative 2 plus square root of 2, negative 2 plus 2 square root of 2, with lambda 1 equals negative 3 plus 2 square root of 2, and lambda 2 equals negative 24 plus 16 square root of 2. So that's one set of solutions, and the other is going to be negative 3, oh, sorry, that's our lambdas. It actually looks like I can be a little lazy. Laziness is about to happen. It's just all these except the minus sign instead. So that makes life a little easier. Okay. So we have our points and our lambdas, and now we want to construct this giant Hessian matrix and then do some stuff. So we're going to construct our Hessian. Hessian of L, basically the Hessian of what we call the Lagrangian. It's going to be a k plus n by k plus n matrix. So in this case, k, we have 2 constraints and we have 3 variables. Okay, so now we're going to take a look at what, in order to find the Hessian, remember we needed the matrix of partial derivatives for G. We also needed the Hessian of F, which in this case, okay, before we go on, we also did a check in the last video that this upper matrix doesn't have a determinant of 0. Problem is, it does. So it's 2x minus 2y. That's going to be 0 when x equals y, which is problematic. We should really reorder the variables, and it looks like if you stick 2z there instead, it should be fine. So if you switch y and z, you should be good to go. However, the text didn't do that, so we're just going to decide to not worry about it and hope it's not a problem. So let's go ahead and calculate this Hessian. And maybe, since the book didn't worry about it, maybe it means you don't actually have to reorder the variables, but wouldn't you rather be safe than sorry? I don't know. I'd rather would be, so. Anyhow, the Hessian we would get, this is going to be the same Hessian we got earlier, 2, 0, 0, 0, 2, 0, 0, 0, 2. But now the Hessian, we can't just take the Hessian of G, we have to take the Hessian of G1 and G2 separately. So the Hessian of G1 is going to be, we'll have 2, 0, 0, then we'll have 0, 2, 0, 0, 0, negative 2. And the Hessian of G2 is just a whole bunch of zeros, because everything is constant there. So that's really nice. So when we do the Hessian of F minus lambda 1 times the Hessian of G1 minus lambda 2 times the Hessian of G2, we're going to get 2 minus 2 lambda 1, 0, 0. 2 minus 2 lambda 1. Oh, sorry, 0. 0, 2 minus 2 lambda 1. 0. And then we'll have 0, 0, 2 plus 2 lambda 1. Okay. So we have that piece. And now we're ready to go ahead and put together our big Hessian of L. Oh, but I scrolled so that I couldn't see the matrix. There we go. We're good. So for a Hessian of L, we're going to have a block of k by k zeros. So k in this case is 2, so we're going to have a 2 by 2 block of zeros. Then we're going to have the negative matrix of partial derivatives for G. So that's going to be negative 2x, negative 2y, positive 2y, or positive 2z. Negative 1, negative 1, 1. We'll have the transpose of that here, negative 2x, negative 1, negative 2y, negative 1, 2z, 1. And then here, we're going to have the Hessian of F minus lambda 1 Hessian of G1 minus lambda 2 Hessian of G2, which was just 2 minus 2 lambda 1, 0, 0, 0, 2 minus 2 lambda 1, 0, 0, 0, 2 plus 2 lambda 1. And now we want to look at, so we have our big Hessian matrix, and we're looking at the sequence di, or negative 1 to the k di for I from 2k plus 1 to k plus n. 2k plus 1 is 5. K plus n is also 5. So really, we're just looking at negative 1 squared, because k is 2, times the determinant of, or times d5. And d5 is just the determinant of the whole Hessian. So we're really just looking at the determinant of all of HL. I don't want to do that. You don't want to do that. But the book told us very specifically that for the plus, if we use the plus signs, you're going to get a determinant of 120, or well, we'll just give the approximate number. It's going to be about 37.49. And using minus signs. Using plus or minus signs, remember we wrote all of this as plus or minus, so that's going to be about 218. So they're both, since we have a positive sequence, it turns out it's only one term, but it's still a positive sequence. Since they're both positive, both are local minimums. And you can find out by just checking them that this ends up being the closest. Check distance. This one is closer. Which shouldn't be too surprising because we have negative plus something, negative plus something, negative plus something should be smaller than negative minus something, negative minus something, negative minus something. Absolute values should work in our favor there. So we see that we have our closest point is going to be this negative 2 plus square root of 2, negative 2 plus square root of 2, negative 2 plus 2 square root of 2. That's going to be our closest point, and we're done. So the main point of this video, even though it got a little long, was just to show you how to put together this Hessian when we have more than one constraint. Obviously, the equations get horrible when that happens, but, you know, we can still do it. So there you go. There is a Hessian problem with a little bit more constraints.